Okay, and we are here again with the open discussion and the question answering. Okay. Now we can answer the question for the authors, and we can start right with the question from Gunel to Niranjana. She asks, when applying mutation operators, did you perform multiple runs or only one?
Yeah, thanks, Gunal, for your question. We do perform multiple operator on every fault injection. We perform around 1,000 injections, and then we retrain after each time. That's why the experiment took a lot of time, and then we look at the results. Yeah.
Okay, perfect. Let's see if we have other questions. I am interested about the interplay between the two papers that you presented. Do you think it's possible of doing mutation targeted to the weak slices only? It's for both of the authors, this question.
Okay, could you repeat?
Yes, Niranjana, please.
Yes. Okay,
Do you think that, do you think that doing a mutation that is targeted to the weak slices, could it be more successful, more efficient than the random one?
Yes. So in one of the experiments, we saw that usually more directed mutation is more effective than random at creating SDCs. So regarding that, I definitely think so. Perhaps one of the authors of the weak slice paper also could comment on this.
Okay, Orna.
I think definitely this is an interesting direction. This is one of the things that could be done, targeting the weaker slices with mutation testing, for example. So, yeah.
That's a good match between the two papers.
Yeah.
We have actually another question from Gunel to Niranjana. What SDC rate you treat as acceptable in your work?
So measure SDC rates is that we treat as acceptable. So we look at the number of we just observe the SDC rates, but I think considering for each fault type, we would say that if the SDCs are greater than 20%, that means that it's no more due to because of there could be SDC because of the model corrected wrongly. But if it's generally more than 20%, we say that that's SDC because of the fault, purely because of the fault.
Okay, thank you.
Yeah.
And from Andrea, it's to Samuel and Orna. Model updates are a bit expensive, as we have seen today. And deciding when to update is a sensible matter. So how often do you check for drifts?
Right. So that's exactly the motivation, right, for drift detection. It's actually to only do model updates once drift is detected, right? So it's on the one hand it's timely, and on the other hand this is not the constant retraining that some people suggest as a solution, right? So how often we check for drift depends on the data, the rate of the data that comes in, because we need sufficient data for all the statistical tests. So you can think about it as sort of ongoing drift detection. And depending again on how much data there is and the result of the drift detection, there will be a suggestion for an update. But first of all, there's also a human in the loop, right? So someone has to go in, check and validate the results, right? We give certain examples, and they can go over them and see whether indeed the predictions of the model were incorrect, right? And the drift detection says it's the error rate is too high, and then they can decide to retrain, okay, to update the model. So this is not an automated action. A human in the loop needs to validate it.
You thought about strategy.
Yes, but it's a difficult task, right? Because one of the underlying challenges is that we don't have, in the domains we're working, we don't have labels in real time. It's difficult and expensive to get the real labels, right? An expert has to come in and label the data so we know if it's a real drift, right? We don't want to have mistakes. So the directions we've been taking have to do with risk mitigation, right? So taking sort of a reasonable time frame that has to do with the question of model updates are expensive, right? So you should have some default where say you at least once a week you update your model, unless there has a drift detection earlier, and then actions there. And it has to do also with the fact that usually we're talking about supervised learning. So to update the model, you need to anyhow label more data, right? So that's part of the decision of when to update the model, and the labeling part, again, that cannot be automated. There are various ways to suggest labels, right? Have weak labels and all of that, but for training, really, a human has to label at least a representative sample. So it's not a fully automatable task, I think. Unless someone has ideas, I'd be very interested in hearing.
Okay, I have another question from Niranjana from Gunel. The mutation operators you use need to retrain the model each time when they are applied.
Right.
This makes your approach expensive because of the several retrainings. Do you have any future work in mind to make this approach more cost effective?
Right. Thanks, Gunath. So even when doing the experiments, this was something that we encountered because we are looking at data falls, and for kind of mimicking data falls, we need to have the fault perform on a fresh copy of the model. That's why we retrain after each time. So the way that we are looking at data falls is that's what influenced the decision to retrain the model each time after each data fault application. So the future work which can be done is to kind of see if we can kind of come up with a representative way in which all the mutations when the data falls are applied can be kind of represented in a comprehensive manner. So if we can represent the effect of data falls on after each training, if we can represent that, then I guess that would make the approach simpler. But we built models that can be distributed flow GPU training, and that's how we were able to do it in a manageable time. But yeah, these are just two of the directions that we can work on in the future.
Indeed, a big challenge to all of us. I have another question for Orna by Andrea. Have you observed the concept drift that should not be incorporated because they represent anomalous data instead of novel nominal classes?
Yeah, absolutely, right. This is one of the many challenges in drift detection, right? There is periodicity, for example. right? That you shouldn't really update your model and always be lagging behind what's happening, right? And there are anomalies, and there's just a point in time behavior that changes back, say a day after. So first of all, this is challenging and it happens, okay? One of the ways we've been trying to address it is to have drift detectors to detect various types of drift. So you try to define the type of drift that's interesting and relevant. For example, out-of-domain examples, right? We've heard about that today as well. One of the common ones. And you tune your drift detector for that, okay? And you can have various detectors that are sensitive to various types of drift, and try not to be sensitive to the types of drift you want to ignore. But for that, you sort of need to make a decision and be aware of the type of drifts you're interested in, and that's not always something that's known. Okay, so it's not always correct.
What about in space? So can the model have different drifts in different geographical areas?
Absolutely, absolutely, and we've actually seen that, right? When people try to take a pre-trained model, for example, types of cellular companies, they take one model and now they try to use it in a different geography, banks, and it nearly always fails. Okay, and it fails because of factors they were not aware of that change among the geographies. Okay, so the best we can do is first of all try to experiment with different types of drift that we can think of, and then put the detectors in place once it's deployed to try and as quickly as possible say, hey, look, we're getting really different distributions here. Quickly go check your results, right, and see whether you have an issue. And really, you cannot deploy as is. You first need to retrain or update your model.
Do the social aspects influence it in different areas, in different geographical areas?
So what do you mean by social aspects?
Well, there are some social aspects in each country that are different. So they can influence the model performance, and the drifts can be influenced by that.
So again, it depends on what your learning task is, right? Is it affected by social factors of humans? So we've been working lately a lot with chatbots, for example. And they're definitely right. It's always an open space. You're always being surprised. And we heard it from Facebook as well, right? Humans just do bizarre things. So yes. And you need to, and that's also a testing angle, you need to constantly update your regression. You need to constantly update how you measure your performance, right? And I don't know that you can avoid, seeing the effects of that.
Today, I have another question from Jirang. Do you think that the mutation you apply are similar to real faults?
Yeah, thanks, Gaurav. So we modeled the mutations after those in the deep mutation paper, but of course our goal here was different, to just observe the STC rates rather than use the mutant models later for mutation testing. So for the data falls that we have, the three of the data falls that are repeating data, removing data, and the shuffle, these are actually, we found a lot of recent work that shows this, that these types of faults are pretty common in even the popular data sets. I think there was one showing that there are a lot of mislabeled data in the CFAR dataset or the MNIST dataset, and then there were the case of even experienced human annotators who have like mislabeled some of the brain MRI scan images. So mislabeled data is pretty common. It's a common issue, and there's been a lot of work addressing this as well. So this is sort of a modeling after a real world fault. But for the noise mutations and the noise data faults that we have, the 3-4 different types, those are obviously we know that there are a lot of denoising techniques that can easily kind of like sort of blow through these faults. These faults are not a problem, but the reason that we model these faults was that if we can kind of have a calculate and estimate the STC rate for these kind of representative noise types, then we can model them. We can use this, and we can have like a guesstimate on how it will affect even the different noise types, unpredictable noise types, real world noise as well. So so some of the faults, like the label miserror, the repeating data, removing data, these are modeled. These are very close to real world faults, I would say. And the noise types, though they necessarily aren't, we can use them to kind of like evaluate how they might perform on real world faults as well. Yeah. Thanks.
Thank you. I have another question from Andrea. Given all the recent work in the automated repair of neural networks, are you considering small focused network adaptation techniques that do not require training the whole network again? So to tweak a little bit the model instead of retraining.
Okay, yeah, that's actually a very good future direction. We did not consider this in our current work, but yes, that's we can actually, I guess we can try working on that as well.
Okay, but have you also some of your mutation are specific to images, right?
Yes.
Have you also tried to go beyond that, trying some other use cases and some other systems?
Okay, yeah. So currently we wanted to come up with this tool and see, if we are kind of getting some predictable results with image. So we started with the most popular image data sets, but definitely the future work including like different types of data like audio, video, text, and all different kinds of the goal would be to expand to all supporting different kinds of data sets as well.
Okay, going back to the previous question, I want to ask also to Orna what she thinks about the tweaking of the model instead of the retraining it.
So this is actually, well, it's in scope and outside the scope of drift detection, right? Because you have to, from the aspect of drift detection, you have to first identify drift, right? And then what you do depends on, what's available to you in terms of the architecture of the underlying model, right? What is in scope is, if now you want to, say, do a small update or even retrain, what data would you need to get the best results, right? Because again, in our settings, where the labeling is expensive, you cannot ask the user to constantly label the data that's coming in. And we have to be smart about what data they need to examine and then what data they should use to get the best results when updating or retraining. Okay, so that's the aspect I think that has to do with this, right? So one thing is the architecture of the machine learning model. In our case, it's black box, right? It can be, even a random forest or, something like that. It doesn't need to be a neural network, okay? But if it is possible to incrementally update, then we need to give the best examples, right? And the best would be the most anomalous ones that triggered the drift detection, right? So it is tightly connected in that respect.
Thank you, Orna. I want to thank actually both speakers for their presentations. And now we will go on with the panel chaired by On. Thank you.
Thank you.